Performance testing is a crucial aspect of software quality assurance. It ensures that software applications meet the performance expectations of users, evaluating how a system performs in terms of responsiveness, stability, and scalability under different workload conditions. By identifying and addressing performance bottlenecks early in the software development lifecycle, we can prevent costly issues after deployment. Imagine accessing a website and experiencing slow loading times or frequent crashes. These issues can lead to user frustration, loss of revenue, and damage to brand reputation. Performance testing helps mitigate these risks by simulating real-world usage scenarios and identifying any potential performance issues. It is essential for a variety of software applications, from websites and mobile apps to enterprise systems and cloud-based solutions. As software becomes increasingly complex and user expectations continue to rise, the need for robust performance testing has never been greater. By investing in performance testing, we can ensure that our software delivers a seamless and satisfactory user experience. Performance testing encompasses various types of tests, each designed to assess different aspects of software performance. Understanding the nuances of each type is essential for selecting the right tests to meet specific performance objectives. Let's explore some of the most common types of performance testing. Load testing simulates the expected number of concurrent users or transactions accessing an application to evaluate its behavior under normal conditions. This type helps determine if the system can handle the anticipated load without performance degradation. Stress testing pushes the system beyond its normal operating limits to identify its breaking point. By subjecting the application to extreme workloads, we can assess its stability and resilience and determine how it recovers from failures. Scalability testing evaluates the system's ability to handle increasing workloads. This involves gradually increasing the number of users or transactions to determine the point at which performance becomes unacceptable. Scalability testing helps to determine the resources required to maintain optimal performance as the system grows. Endurance testing, also known as soak testing, assesses the system's stability over an extended period. This type of testing helps identify performance issues that may only surface after prolonged usage, such as memory leaks or resource exhaustion. Volume testing evaluates the system's performance when handling large volumes of data. This type of testing is crucial for applications that process or store significant amounts of data, ensuring that they can maintain performance as data volumes increase. By understanding the purpose and impact of each type of performance testing, we can develop a comprehensive testing strategy that addresses the specific performance requirements of our software applications. A well-defined performance test environment is essential for obtaining accurate and reliable test results. The test environment should closely mirror the production environment to ensure that the results are representative of real-world performance. This includes using the same hardware, software, network configurations, and data volumes. Begin by identifying the hardware and software requirements for the test environment. This includes the number and specifications of servers, databases, network devices, and other infrastructure components. It's crucial to ensure that the test environment has sufficient resources to handle the anticipated workloads without introducing bottlenecks. Next, configure the software stack, including the operating system, web server, application server, database, and any other dependencies. Ensure that the software versions and configurations match the production environment as closely as possible. Consider using virtualization or cloud-based solutions to create a scalable and cost-effective test environment. Data plays a crucial role in performance testing. Populate the test environment with realistic data that reflects the production environment's data volume, variety, and distribution. Use data masking techniques to protect sensitive information while preserving the data's characteristics. Once the test environment is set up, we can begin executing performance tests. This involves using specialized performance testing tools to simulate real-world user interactions and generate workloads. Selecting the right performance testing tool depends on several factors, including the type of application, the testing methodology, and the budget. Popular performance testing tools include JMeter, LoadRunner, and Gatling. These tools offer a wide range of features, including test script recording, workload modeling, performance monitoring, and result analysis. They also support various protocols and technologies, enabling us to test different types of applications. Before executing the tests, it's essential to define clear performance goals and thresholds. These goals should be based on business requirements, industry benchmarks, or service-level agreements. For example, a goal might be to ensure that the application's response time remains below 2 seconds under a peak load of 1,000 concurrent users. During test execution, closely monitor the system's performance using real-time dashboards and performance counters. Look for any signs of performance degradation, such as increased response times, high resource utilization, or error rates. Capture screenshots, log files, and other relevant data for later analysis. Section 5. Key performance metrics. Performance testing involves measuring various metrics to evaluate the system's behavior under different workload conditions. Understanding these metrics is crucial for interpreting test results and identifying performance bottlenecks. Let's explore some of the key performance metrics. Response time. Response time measures the time it takes for the system to respond to a user request. It's a critical metric for user experience, as long response times can lead to frustration and abandonment. Throughput. Throughput measures the number of transactions or requests the system can handle per unit of time. Higher throughput indicates better performance, as it shows the system can process more work in the same time frame. Resource utilization. Resource utilization measures the percentage of system resources being used, such as CPU, memory, disk I/O, and network bandwidth. High resource utilization can indicate performance bottlenecks, as it suggests that the system is struggling to keep up with the workload. Error rate. Error rate measures the percentage of requests that result in errors. High error rates can indicate problems with the application's stability or capacity and should be investigated thoroughly. Latency. Latency measures the time it takes for data to travel between 2 points in a network. High latency can impact application performance, especially for applications that rely on real-time data transfer. Section 6. Analyzing performance test results. Analyzing performance test results is crucial for identifying performance bottlenecks, understanding their root causes, and recommending solutions. This process involves examining the collected data, correlating metrics, and identifying patterns and anomalies. Start by reviewing the performance goals and thresholds defined during the test planning phase. Compare the actual test results against these goals to determine if the system met the performance expectations. Identify any deviations from the expected behavior and investigate further. Next, analyze the performance metrics collected during the tests. Look for trends, spikes, or anomalies in the data that may indicate performance issues. For example, a sudden increase in response time or error rate could point to a bottleneck in a specific component. Use performance profiling tools to identify code-level bottlenecks within the application. These tools track the execution time of different methods and functions, highlighting areas of the code that consume significant resources. Profiling helps pinpoint the root causes of performance issues, enabling developers to optimize the code effectively. Document all findings and observations, including screenshots, log files, and relevant data points. This documentation will be valuable for communicating the results to the development team and tracking the progress of performance improvements. Effective reporting and communication are essential for conveying performance test results to stakeholders and driving remediation efforts. Performance test reports should be clear, concise, and actionable, providing insights into the system's performance and recommendations for improvement. Begin by summarizing the test objectives, methodology, and test environment. This information provides context for the results and ensures that all stakeholders understand the scope of the testing effort. Include a summary of the key findings, highlighting any performance issues identified during the tests. Present the performance metrics visually using charts, graphs, and dashboards. Visualizations make it easier for stakeholders to interpret the data and identify trends or anomalies. Use clear and concise language to explain the metrics and their significance. Provide specific recommendations for addressing the identified performance issues. These recommendations should be actionable, prioritized based on their potential impact, and assigned to the appropriate team or individual for resolution. Regularly communicate the test results and progress to stakeholders through meetings, email updates, or dashboards. This keeps everyone informed about the system's performance and ensures that any issues are addressed promptly. Defects identified during performance testing require careful management to ensure they are addressed effectively and efficiently. Establish a structured defect management process that includes defect tracking, prioritization, assignment, and resolution. Use a defect tracking system to log, track, and manage performance-related defects. Capture relevant information, such as the defect description, severity, steps to reproduce, test environment details, and any supporting evidence. Assign each defect to the appropriate developer or team for resolution. Prioritize defects based on their severity and impact on the system's overall performance. Critical defects that significantly impact functionality or performance should be addressed immediately. Lower priority defects can be scheduled for resolution in future releases. Collaborate with the development team to investigate and resolve performance defects. Provide developers with all the necessary information to reproduce the issue and identify the root cause. Work together to identify potential solutions and implement the most effective fix. Once a defect is resolved, retest the affected functionality or workload to verify that the issue has been addressed. Update the defect status in the tracking system and notify stakeholders of the resolution. Here are some best practices for conducting effective performance testing. Start early by integrating performance testing early in the software development lifecycle to identify and address performance issues before they become costly to fix. Define clear goals by establishing performance goals and thresholds based on business requirements, industry benchmarks, or SLAs. Use realistic workloads to simulate user workloads and data volumes that reflect the production environment. Monitor the system's performance continuously during test execution to identify any signs of degradation or bottlenecks. Analyze results thoroughly to identify bottlenecks, understand their root causes, and recommend solutions. Communicate effectively by regularly updating stakeholders on test results and progress, using clear and concise language. Automate where possible to improve efficiency, repeatability, and coverage. Use the right tools that are appropriate for the application, testing methodology, and budget. Foster collaboration between developers, testers, and operations teams to ensure that performance issues are addressed effectively. By following these best practices, we can establish a robust performance testing process that helps deliver high-performing software applications. Performance testing is an integral part of software quality assurance, ensuring that applications meet user expectations for responsiveness, stability, and scalability. Through a combination of different performance testing types, a well-defined test environment, appropriate performance metrics, and effective analysis and reporting, organizations can identify and address performance bottlenecks early in the SDLC, preventing costly issues after deployment. By prioritizing performance testing and incorporating best practices, organizations can deliver high-quality software that provides a seamless and satisfactory user experience, leading to increased customer satisfaction, improved brand reputation, and ultimately, business success.